afternoon at the same time. So that's the advantage of the webinar, that it can be seen all over the world. I welcome you to my talk about the ISO 4037, which was revised in 2019. Today we will talk about what is new and why do we have to change. Overview, as I said, it will give us the motivation for the revision. We'll talk about the problems we had with the previous revision or previous version, the requirements, which are sometimes harder, sometimes more relaxed, and why, and easy how to set up your lab by using this ISO as a cookbook. We will talk about the terms matched reference fields and characterized reference fields, and we will have a look to the conversion coefficients for matched fields and how to determine them for characterized fields. Then we will have a look to the challenges and future research topics, and by far not all problems are solved today. Why do we need reference fields? Artificial reference fields are needed to perform reproducible and traceable tests. That means if I have an instrument under test, an active area dosimeter, a pulsal dosimeter, a passive eye-lens dosimeter, or a fingering dosimeter, and I want to perform IC or ISO type tests, I have to ensure that the results will be independent of the laboratory where the tests have been done. So therefore, they all have to use the same radiation quality to get the same results on the same device. And that's the reason for the reference fields and why we have defined them. And the tests also have to be valid for the real radiation situation, because it doesn't help if you have a test and the device performs perfectly, and if you are in field, the device fails to measure the dose. So therefore, it must be applicable for it. The ISO standard defines X and gamma reference radiation for the calibration of dosimeters and dose rate meters, and for determination of their response as a function of photon energy, independent of the type of device. If I want to test an instrument, the best would be using monoenergetic radiation. That's difficult to get. You can go to a synchrotron, but going to a synchrotron for every device is not feasible. So therefore, the first idea is to use X-rays. The problem with X-rays is that you have a broad energy distribution. But fortunately, by applying absorber or filters, you can reduce the width of the energy distribution. Unfortunately, at the same time, you also reduce the dose rate or the fluence shown in this figure, depending on the quality we have defined. You have a high air camera rate with a broad distribution. You can use filters to generate the wide spectra, or the mostly used narrow spectra, which is an optimum for still having enough dose rate, but having a reduced energy distribution. Or for special cases, you have the low air camera rate series. The series are defined in that way that if you add up all these qualities, you will get an energy distribution which is similar like a rectangular shape. So you really have a possibility to test the whole energy range with nearly the same step size. That's the reason that the qualities or the filtration is in that way defined, that you get a nearly linear dependence of the mean energy of the spectra with increasing high voltage. Testing with N series covers the worst case, because this is, we say monoenergetic. By far it is not monoenergetic, but it is assumed as monoenergetic. And if you have performed this test with this N series, you can be sure that at broader workplace fields, the performance of the device will even be better. That means if you have to test an eye-lens dosimeter, which is normally used in radiology with RQR series, You can perform the test with N series, and you can be sure that the device will perform better in these radiation fields. Having a look to the history, part one, when the requirements have been set for the reference fields, was oriented on air camera. In '96, the Euratom directive came up with the phantom-related radiation protection quantities, so that was a big change. In '97, the part 2 with dosimetry was published. In '99, part 3 with the conversion coefficients was published to cover this Euratom directive to include the conversion coefficients. As the technique goes on, the design of the high voltage generators was changed. So in former times, you had a lot of problems with ripples, and it was more AC high voltage than DC voltage. So with the upcoming high frequency generators, it was more stable. And in fact, the spectra changes, and with changing spectra, the conversion coefficient changed. This was be shown by, for example, there are many publications. An example, as I'm from PTB, it's PTB DOS 34, which is available from our website. It was a spectrometry of the new generation of X-ray generators, and it shows that the conversion coefficients change, especially for low energies. This knowledge was put into part 4 to make aware of this. And in 2012, it was, in fact, it is ISO 4030 part 0, but you can't call it in that way. So it is called ISO 29661 and an amendment, which gives the definitions and fundamental concepts used for the 4037. In 2015, we published the 18090 part 1 for taking into account the pulsation of the field. And do we really need it a revision? If you have a look to the half value layers, which are determined for air camera with the old generators, so published half value layers in ISO, with the new generators, you will see that at high energies, you don't have a problem, so there is no change. But if you go to the low energy part, you see that below 30 kV, there is a big difference, or the ratio is increasing for the new high half value layers. And it's up to 20%, so that makes a problem. That's for air camera. What happens for the radiation protection quantities? The conversion coefficients, the monoenergetic conversion coefficients, show a strong energy dependence, especially at low photon energies. And for sure, the chain also depends on the tissue depths. If you have a look to them, you'll see that is at high energy part, this is only the backscattering from the phantom. That is nearly similar for all tissue depths. But if you go to the low energy part, below 30 kV or below 20 kV, you will see that there is a dramatic difference between them, because 0.07 means it's nearly air camera, so it is nearly 1. But 10 millimeter tissue means already a huge amount of absorption. And this gradient comes additionally to the change of the high voltage or to the spectra on top, and leads to the fact that the conversion coefficient for the new generation of generators is nearly a factor 2 different from that published in the ISO from 1999. In fact, that means, and that happens, that if you have a dosimeter which tests it at a lab using the old conversion coefficients, will fail the type test. If you use the new conversion coefficient for the new X-ray generation, this instrument passes the type test brilliantly. That was the reason that we decided that the revision is really needed. In fact, the structure remains the same. So part 1 describes the characteristic and production methods. Part 2 describes the dosimetry. Part 3 is calibration and conversion coefficients. And part 4 remains with special requirements if you go to the low energy part. Unchanged also remained that the mean photon energy is related to spectral photoinfluence. The spectral resolution remains to spectral photoinfluence. The half-value layer thickness depends with respect to air camera. It's the same for the old version. And the homogeneity coefficient, that is the ratio between the first and second half-value layer thickness, is also still to respect with air camera. So the characterization of the field is still done in air camera. What changed? So we included the new 29661. We have extended the W and H series to low energies, and we have extended the N and H series to 400 keV. So we have new qualities. The high voltage should be measured with a high voltage divider instead of using spectrometry, and the old possibility to adjust the high voltage is not needed anymore, because if you follow these requirements, you don't have to adjust the high voltage to fit the half-value layer. What also has to be taken into account is that some X-ray tubes have a protective resistor, and it's in line with the tube. That means with increasing tube current, there will be a voltage drop on this protective resistor. That means that the high voltage at the tube is lower than expected, also changing the spectra. So we have to take care about this. For the build-up plate, there are two new requirements. So first of all, the most important, it's only 3 millimeters for cesium and cobalt, so you can't mix up them anymore. And they have to be positioned as closely as possible to the dosimeter. I will show something later. And the conversion coefficients are now given for all quantities. That means for 3 millimeter depths as well. And it's given in 15 degrees steps instead of 10 degrees, because for the type test requirements, you always need 15 degrees steps. The requirements in this standard are chosen to ensure an overall uncertainty of 6 to 10% for the dose rate of the phantom-related operational quantities, instead of air camera as it was done in the 99 version. Every value and every requirement is now traceable to a publication. This was also not the fact in the old version. And now we have this matched and reference and characterized field. So the scope defines the characteristic and production methods for calibrating protection level dosimeters with respect to the phantom-related operational quantities of the ICRU. So for sure, the old quantities, not the one ICRU is publishing at the moment. The lowest air camera rate for which the standard is applicable is 1 microgray per hour, because at lower energy, lower dose rates, you have to take care about the background radiation. This will be done in a new ISO standard, which is at the moment under preparation. For radiation quality specified, sufficient published information is available to specify the requirements for all relevant parameters for matched and characterized reference fields in order to achieve the targeted overall uncertainty. The X-ray radiation fields described in the informative Annex A and 2 are not designated as reference radiation fields. That's an important change, because there are qualities which the requirements are not exact enough to state them as a reference field. That means that, example, the fluorescence radiation and the 241 americium source, the R titanium and R nickel, are removed from the main part, but are kept in the informative annexes A and B. So they are available, but there are no more reference fields anymore because they can't fulfill the requirements. What is a matched field? A matched reference radiation field reference radiation field whose properties are sufficiently well characterized so as to allow the use of the recommended conversion coefficient. So if you have a matched field, you can use the conversion coefficient mentioned in the ISO. A characterized reference field is a reference field whose properties are not sufficiently well characterized so as to allow the use of the recommended conversion coefficients, but the mean energy of which is close enough to the nominal value to be used as a reference radiation field with a given designation. That means that you still have a reference field, so the mean energy is close enough, but the spectral shape is a little bit different, and you have to determine the conversion coefficient by yourself. How to set up a lab? So it's quite easy. First of all, you have to purchase a high voltage generator, X-ray tube with the requirements mentioned in the ISO. You have to buy the filters with the material, impurity, thickness, also mentioned in the ISO. Construction of the equipment, determination of the inherent filtration, and you have to purchase the additional filters to adjust the inherent filtering. So you need the generator, you need the high voltage divider, you need the tube, the monitor chamber, the filters, the turning table, and you buy it according to ISO 4037 Part 1 requirements, which are mentioned, for example, in 4.2.1, characteristics of the high voltage generator, the tube potential and protective resistor, the filtration, inherent and additional filtration, the X-ray shutter, and the beam aperture. So in fact, for all these things, there are requirements which have to be fulfilled. Let's have a look to the requirements. Here I've shown the requirement on the relative change of the high voltage tube potential for HP10 and for HP3. The first point is that you see that the requirements will depend strongly on the quantities you want to realize. That means you may have an instrumentation which fulfills the requirement for HP3, but will fail to fulfill the requirements for HP10. If you intend to realize HP10, then you can stick only to these requirements, because if these requirements are fulfilled, they are automatically fulfilled for the less challenging requirements related to HP3 or HP 0.07. What you see is we have calculated from the gradient of the conversion coefficients the change of the high voltage, which would imply a change of the conversion coefficient by more than 2%. And if you do it for different high voltage, for different energies, for different high voltages, you will come up with this behavior. And from this, a step function was found, which is taken in the ISO. The total filtration comprises the inherent filtration given by the tube and the additional filtration to realize the radiation quality. The inherent filtration should be adjusted at a high voltage of 60 kV because you are aiming an aluminum equivalent, which is only aluminum equivalent at a given energy, so we have to specify the energy. The tube window is limited to 10 millimeters beryllium, because if it's bigger, you get a lot of scattered radiation. And the requirements on the relative change of the filter thickness depends on the radiation quality, the same as for the high voltage I've shown. We can do it for the filtration as well, depending on the thickness of the filter and the series. That means the type of filter, if it's aluminum, copper, tin, or lead. You will have different requirements, different for the different quantities. And from this coming up, we find some requirements taken into the ISO. With this, now you have your installation, and the next step is you have to validate your installation. And that's a question if you are a secondary lab or if you are a primary lab. If you are lucky, you are a secondary lab, it's quite easy. You just have to buy some instrumentation and do your measurements. So you have to purchase traceable calibrated air camera chamber and HB10 or H*10 chamber. So HB10 chamber can be bought easily. The validation of any radiation quality with these chambers according to the requirements in the ISO. And then you perform later, after validation, your irradiation with and without phantom, depending on its HP or H*, measuring Ka, also the air camera, at each irradiation with the air camera secondary standard chamber and apply the recommended conversion coefficient, or you also can use a calibrated monitor chamber. So you can measure air camera, apply the recommended conversion coefficient, and then you get the phantom related quantity. Or you directly measure the phantom related quantity by using a suitable secondary standard, or you can also calibrate your monitor chamber in this quantity. If you're a primary lab, then you have to buy not an ionization chamber, you have to buy a spectrometer, because you want to achieve lower uncertainties. Therefore, you have to have a closer look to your spectra. Some requirements are described in part 2 related to the spectrometer, then measurement of the spectral distribution of the corresponding series and calculation of the conversion coefficient. So you don't use those tabulated in the ISO, you have to determine your own conversion coefficients. Then you have to use your primary, secondary standard chamber to determine the air camera dose. And for the irradiation, it's a similar approach. So you have to determine the air camera by using a primary or secondary chamber, and then you have to apply the measured or the calculated conversion coefficients. And for sure, this also can be done by the monitor chamber. So the main difference is that you have to perform spectrometry. In part 2, there are some requirements on spectrometry. As spectrometry is not so easy, we have the proposal for a new work item proposal in ISO, measuring and calculating methods of the spectral fluence distribution at the point of test, calculation of conversion coefficients from air camera to dose equivalence. There we want to set up a standard giving a guideline how to perform spectrometry, how to characterize spectrometer, and how to do the unfolding. Coming from X-rays to the gamma radiation emitted by radionuclides, there are also requirements on the capsulation, on the air camera rate due to impurities, so radiation outside the collimated beam, the minimum final distance from the aperture, and also from the wall to avoid scattered radiation. You have to check the fulfillment of the inverse square law, and you have to care about scattered radiation from your collimators. There's also a scheme given how to construct a collimator to get rid of scattered radiation. What is new, you also can use not only different radiation sources for different dose rates, you also can use one source and using different lead attenuators to reduce the dose rates. What is not more included is the uncollimated geometry. So we have decided that this is no more a reference field. Very special is the high photon energies for MeV to 9 MeV. They are produced by a proton bombardment of targets, so calcium fluoride target or Kohlenstoff target. The necessary dosimetry is also described in part 2. And to my knowledge, there are only 3 facilities in the world, one at PTV with CMC entry, one in Japan, and one is in France. The ISO part 2 describes a procedure for dosimetry of X and gamma rays for the whole energy range. This document can also be used for dosimetry for the radiation qualities which are not more reference radiation qualities, but they do not become reference radiation qualities by using the standard. For the reference field, the existence of only a small difference in the spectral distribution of the matched reference field compared to the nominal reference field is validated by procedures which are given and described in detail in this document. For matched reference radiation fields, recommended conversion coefficients are given in part 3, and only for specified distances between source and dosimeters. For other distances, the user has to decide if these conversion coefficients can be used. So we have to decide that we define them at special distances, but for sure they can be used at any other different distance as well, but then you have to think about what you are doing. The second method is to produce characterized reference fields, either by this is done by determining the conversion coefficients using spectrometry, or the requirement is measured directly using secondary standard dosimetry. This method applies to any radiation quality for any measuring quantity and, if applicable, for any phantom and angle of radiation incidence. The conversion coefficients can be determined for any distance provided for the air gamma rate is not below 1 microgray per hour. So that's the limitation of the standard. Both methods required charge particle equilibrium, so that's an important topic. This document specifies part 3, additional procedures and data for the calibration of dose rate and dosimeters. The general procedure for the calibration of and the determination of the response of radiation protection dosimeters is described in this 29661. In Annex D, additional information on reference conditions, required standard test conditions, and effectors associated with electron ranges are also given. For individual monitoring, both whole body and extremity dosimeters are covered, and for area monitoring, both portable and installed dosimeters are covered. I think that is important, that you can calibrate any dosimeter. Charge particle equilibrium is needed, needed for the test, although it is not always established in the workplace field for which the dosimeter should be calibrated. So that's a topic for ICRU to propose new quantities. The procedure to be followed for the different type of dosimeters are described. Recommendations are given on the phantom to be used and on the conversion coefficients to be applied. Recommended conversion coefficients are only given for matched reference fields. And informative Annex A, B, and C conversion coefficients are given, but only as a rough estimate, as the overall uncertainty of these conversion coefficients and practical reference field is not known. So if you still use this not reference fields, you will find a guideline which could be the conversion coefficients, and you can use them by enlarge your measurement uncertainty. For sure, it's not reference field, but you get values. The recommended conversion coefficients needed charge particle equilibrium, what that is, and the positioning of the build-up plate. There's a publication, we made investigations on this, and we found out if the build-up plate is far away from the dosimeter and you have a dosimeter with a thin entrance window, you don't have charge particle equilibrium, and therefore now you have to place it. So this is all published. You can read it by your own. Just to show you the effect, so have a look to cobalt. So if you have a built-up plate of 3 millimeters and it's in close contact, that's the normalization point, and you go away with this built-up plate, for example, 15 centimeters in the old, as in the old version, you can be off by 20% because the amount of secondary electrons is missing. And if you are far away, it's the same as if you don't use a built-up plate, you can be off by 40, 60%. For sure, this also depends on the distance from the source. If you are far away, you have a lot of air, there's air scattering, so building up electrons, so then you get charge particle equilibrium without built-up plate. But this is very difficult, and it would depend on the distance and so on. It was decided, use 3 millimeter built-up plate in any case, and you will be always in the right situation. Let's come to the photons. So our measurement quantity is defined in that way that it is in the person. So we have to substitute for measurement the person by any kind of phantom, and ICRU has been done this by using this ICRU sphere. This ICRU sphere is then directly used to calculate the ambient dose equivalent H*10. As a person is part of the definition, and we have personal dose meters, how can we calibrate them? Because we are not allowed to put the person inside the radiation field, and the quantity depends on the person. If you have a thin person, the HP10 value will be different from a thick person, and this is for calibration quite difficult. So you have to replace the person by a phantom, by a standard phantom. And as the ICRU sphere would be not good for calibrating several dose meters at the same time, they decided to replace the sphere for the personal dose equivalent with this slab phantom with 30 centimeters times 30 centimeters times 15 centimeters, made of ICRU tissue. So it's only used to calculate the conversion coefficients. So please, never try to buy an ICRU phantom. You will fail because this ICRU material is artificial, only used for Monte Carlo simulations, and cannot be produced. If it cannot be produced, how to solve this? We'll come to this later. So for sure, they defined it for HP10, for the pillar, and also for the red phantom for fingering dosimeters. And this is for the wrist dosimeters. ICRU tissues are not available, but we have to perform calibrations on phantoms. Now that's a point ISO comes in. So from the ISO point, we substitute this ICRU tissue phantoms by adequate phantoms, which will be similar concerning the backscattering, but not due to the absorption. That means if you have irradiation from the back 180 degrees, this will be not in accordance with this ICRU phantom. That's the reason that in ISO 4037, the conversion coefficients are limited to 90 degrees, because you don't want to go through the phantom. It's only the backscattering you are interested in. And that set of phantoms which ISO defines, so it's our ISO water slab phantom. Now we have the ISO water cylinder phantom for the eye lens dosimeters. This is quite new. We have the pillar phantom, and we have the ISO rod phantom. As ICRU defined it, always 300 millimeters, and handling a 300 millimeter rod phantom is quite difficult. And if you have a small dosimeter, the contribution from the far end of the phantom might be negligible. There have been investigations, and I found out that if you use a 10 millimeter heights, that is quite sufficient. And as you can't buy 90 millimeters PMMA in diameter, you have the possibility to use plus minus 1 millimeter, and it's still in accordance with the Becker's scattered radiation. So this is the theoretical phantom, but you also can use this, and that's what is included in the new version of the ISO as well, because it's the practical solution. So now we have the phantoms. If we have the dosimeters, we can replace the persons and put the dosimeters under well-defined conditions to calibrate them all. As I said, part 4 will care about the low energy part, additional aspects of the characterization of low energy photon radiation, and the procedure for calibration and determination of the responsive area and personal dosimeters as a function of photon energy and angle of incidence. Especially if you have a look on the angle of incidence and you go to the very low energies, then you come up with the requirements to adjust the angle of incidence with an accuracy which is not achievable anymore. So that's the reason that this part 4 mentions this again. And this starts already if you have an N20 quality and you have 75 degrees angle of incidence. It is nearly impossible to achieve the accuracy to adjust the angle of incidence. So I invite you to have a look to part 4. There's a table with the requirements, and it's really fascinating. This document concentrates on the accurate determination of conversion coefficients for air camera to the quantities and for spectra of low energy photon radiation. As an alternative to use conversion coefficients, the direct calibration in terms of these quantities by means of appropriate reference instruments is described. Yes, as I said, table 3 states values for the requirements on the angle accuracy. It's really interesting, and you wouldn't believe it before you look to this table. At low energies, the air density dependent absorption changes. So if the air density change, for sure the dose rate changes. But at the same time, the shape of the spectra also changes because the absorption for the low energy part is much higher than for the high energy part. That means if you have a different shape of the spectra, you will also have a different conversion coefficients. If you are above 30 kV, you don't have to care about this. But if you go to low energies, you also have to care about this point. Therefore, in Annex A, there is a method stated how you can correct for this. As I said, not all points are solved up to now. So many of the requirements are based on calculations, especially for the half value layer determination. We came up, if you can determine them, of 2 methods. You can use the spectrometry and calculate it out of the spectra, or you can perform dosimetry. And I would believe in both you would end up with the same half value layer thickness, but that's not the case. So there are several investigations which show that there is a difference of nearly 2%. This is also mentioned in the ISO. So we'll find that the note that even if you are 2% off, depending on the method you have used, it is okay. I don't know why, and I really would like to find out it. So this is a research topic, and maybe for a research mobility grant, we will find out this. Influence of filter thickness. We had within the dose trace a training, hands-on training in the lab, and from the theoretical point, We modified the filter thickness and performed the experiments, and we found out that the experiment is much more insensitive to the filter thickness than expected from the theory. I don't know why, and this is also a topic for future research. It is proposed to use a secondary standard for the phantom-related quantities to determine the dose. This could work. Unfortunately, I haven't done many measurements in that direction to be really sure what is the remaining uncertainties by using this alternative approach. In fact, all the secondary standards are not measuring the quantity itself. They have an energy response which closely follows the behavior of the quantity. So therefore, there's also a variation. If you buy two HPTM chambers, they might be a bit different at low energies. It's interesting. So that's also future research we have to find out, and maybe a new revision will be necessary. Well, let's see. What we have learned today. So all requirements are traceable to publications. I've shown some publication for the requirements on filtration, filter thickness, and positioning of PMMA plate. For the PMMA plate, it is decided to use 3 millimeters instead of 2 or 4 millimeters. So you can't mix up it anymore. The absorption due to the build-up plate is less than 1% for the 3 millimeter plate. Therefore, you don't have to care about this. Is also stated in the ISO. The new version takes into account the actual generation of X-ray generators. For sure, if you have quite old ripple generators, you shouldn't use this new conversion coefficients. It proposes 2 methods for realization of reference fields, and it gives recommended conversion coefficients in the case that you have matched fields. For sure, if you have a primary lab, you have to determine your own ones. And it still offers possibility for future research. Thank you, and I hope you have enjoyed the talk, and for sure you will have a lot of questions, and maybe some of them I can answer.